So I will start my second lectures by reminding our main result. This is due to myself and Park. Let's think about Q, who is any smooth point of X, and we are consider the inner projection from Q. Then the first result is so-called embedded linear syzygy. It means for this one we don't have smoothness assumption for any point. Then there is a natural inclusion of syzygy Tor module from Tor this means the coordinate link of the projected image to the piece Tor module of original one. Every phi. So, in other words, so the graded Betti numbers in the first linear strand of the XQ is not greater than to the graded Betti number of original one, phi, and in particular our definition Bx is not greater than equal to B. Bxq is not greater than Bx. So I remind the definition of Bx and Ax. So if we consider the minimal free resolution of coordinating of some projective variety, then we have the following Betti table. Blah blah. And now we are focusing on the first linear strand of this one. So by Ax, we denote Ax by the number, how the MP property is going further. And this is directed Ax, and this position directed by Bx. So there are this relation between Ax and Bx, A and Xq. And this is for. So in Eisenberg, Green, and Hulik-Popescu, they are considering the behavior of syzygy under some taking section, and they have some kind of surjection. And for this kind of inner projection, we have some injections. And second is syzygy on the first Ax minus 1 part. So, and if we say more, the syzygy of the first ax minus 1 part, then let's suppose our x satisfy the nax. It means our ax is some number greater than equal to 1. Then and q, here we taking q is smooth point, any smooth point. Then in this case there is also natural inclusion between two Betti number, but not just linear strand for every Betti number, every q. So in this case we can embed this Betti number for for every phi is less than equal to 2 a minus 1 and q is any numbers. Okay, so this means so this means so beta pq or xq is less than beta pq of x for every p between here and every q. Sorry, you should distinguish these two q. This is represent the point of q, and this is just the index of the Betti numbers. I'm sorry. And this implies some lower bound of ax. This bounded below by ax minus 1. So this is second result. And third result is, this is some very useful inequality. So on the first linear strand, we have also this kind of inequality. So this beta p comma 1 is bounded by beta p minus 1 comma 1 of xq plus beta p comma 1 x plus e choose p, where as our rotation E is codimension of our variety. For this is for any variety x and any p. K variety, and the equality holds for every phi is less than equal to 2 ax minus 1. And we have also formula equality for phi equal ax case. Then the calculation of linear syzygy is involved by the existence of some cubic linear syzygy. Minus so in this case we have equality, and this exists some cubic syzygy is have some effect on this linear syzygy.
I'm sure it appears on the right side, maybe it's SQ and the formula C.
Yep.
No, and the formula C is beta P1X is bounded by...
Yeah, this one?
Yes,
yeah.
The second summon...
Oh, I'm sorry.
Yeah, Q, yeah. Right, okay, thanks.
Yes. Thank you very much. Yeah. Okay. And the final result of theorem 1 is, so we take our Q here, and if the stabilization number of our partial elimination ideal with respect to Q, this is stabilization number of respect Q, then we have this kind of depth formula. So original depth of a coordinate ring is equal to preserved under the inner projections. Yes. Yeah. Okay. So this is our main result, and to study this result, we have the following propositions. I just state the propositions. So if X and Q is smooth point, consider as usual, and the number S also, then in this situation we can relate the NP property of image and original one. So if our original AX satisfies some NDP property for some D is greater than equal to 2S and some P. Yeah, here NDP means so in our Betti table Bx, so first P part, so this goes from 0, 1, 2, and first P part, the height of the table non-zero part is at most D. So D minus 1. Yeah. So if our Betti table has some shape in first P part, the height is within the D minus 1, then we said this has some NDP property. So if our original AX is this property, then we can say the in last lecture we defined K tilde and K tilde of our ideal. So this is stabilization number. So K tilde S minus 1 for this module, we said this is also satisfy NDP minus 1. And conversely, if we know this module, this S1 module satisfies some NDP property for some D is not less than to the S plus 1 and some P, then we can say our original IX as S module, this is satisfy NDP property. So using these two property, we can say we can relate between regularity of two things. So regularity of original one is calculated by the maximum of regularity of our ks minus 1 tilde and s plus 1. Yeah, the proof is given by the elimination mapping sequence and partial elimination ideal theory. But yeah, in our main interested case is s equal 1. So this is some general development. But s equal 1 case, then k tilde ix is become to k0 tilde ix. So by the definition, this is also the zeroth elimination ideal, which means the ideal of the image. So in this case, yeah, and if s equal 1, then we can say from the d equal 1 and 2 case, and every case we think about the relation of original one and the image variety. Okay, good. So using this result, so we can prove this one. Last time I state this result. Yeah. So any variety, first pth higher syzygy, this matching number is bounded by p times e choose 1, choose p plus 1 for every p equal greater than equal to 2, 0, and the inequality holds if and only if x is variety of minimal degree. And with this theorem, we are generalizing some classical result, which also I stated last lecture, but we start state one more. So x is minimal degree. So this is some property about some statement of the degree of the variety, and x or idealship of x is too regular. So this is statement of the Castello-Mumford regularity, and C is beta 1 1 equal e plus 1 choose 2. So this is says number of quadrics. So we also put here C prime means so one of beta p1 achieve the maximum bound. For some p, and next one is all of beta p1 is achieved the bound for all p. So these two things about some maximal Betti number. And last time I forgot this one. The last equivalent statement of this, the A of x equal to the codimension. Yeah, this is called syzygetic rigidity. So we can say some remark. So this theorem 3, this is a characterization is for some extremal variety. So in which sense having low degree and low regularity and maximal petty numbers in the partially linear stance. So this kind of some extremal situation, the low degree and low regularity and maximal petty number, they happen simultaneously and give some equivalence relations. And for this synthetic rigidity is originally proved by the Eisenberg-Green-Hulik-Popescu for general algebraic set. But we still can prove using our inner projection technique. Then for little bit smaller category, we can prove this is also. Okay. And similarly, we can also characterize it next to extremal case, generalizing by Fano's classical result. Like this. So unless our X is variety of minimal degree, then we have the following: beta p, 1 of our X is less than or equal to this number minus for every p between 1 and codimension e, and if p greater than e, then this number is 0. And further, the equality holds if and only if our X is a del Petrov variety. In our talk, this del Petrov variety means not just for linear normal one, but we can think about the projection of the del Petrov. So this is ACM and degree is dimension equal E plus 2. And so, similar to the extremal case, for this next to extremal case, we can also the following equivalence. So first is X is del Petrov. And next one is one of our beta p1 achieve this maximality. For some between 1 and e minus 1, and next thing all of beta p1 achieve these maximal numbers. And first one is ax equal e minus 1. Okay. Okay, so similarly for this next external case, we still have some syzygetic rigidity if our number of AX equal to the E minus 1, and this gives some property, many property of our X. And geometric classification of this variety is mainly given by Fujita and recently Peter Schenger and Markus Broderman and Yu Sung Park. By them, many of them classify by the secant locus with respect to the secant locus of the projection of the minimal degree variety. So this is for next to extremal case. Okay. And when I start the lectures, I erased two questions. So these two theorem is the answer of the first question. And for the question 2, we have some result, the following result, so-called necessary row bound for NP property. So it says if our X suppose that our X has NP property, then the number of quadrics of X, so beta 1 1, it should greater than or equal to this number. So if we maximizing for this low bound, then we can just put in this place of P then AX, then we have some maximized the low bound. This is, you see, this is necessary condition for NP property, so not sufficient condition. But with this low bound, we can some case we can check the failure of an NPness of given variety. So one of my hope is using this bound and some further condition to consider some sufficient condition of NP property, but not yet is successful. So in some case we can check with this bound the failureness of NP property. For example, the NP failure of N7 of triple Veronese of P2. So about the cities of Veronese embedding, maybe Professor Ottaviani is one of the expert. So known result is this one. Known result is triple Veronese embedding of Pn is fails n 3 times d minus 2 for any current. N is not less than 2 and d is not less than 3. And conjecture is this is hold, this is satisfied, and 3 times d minus 3 for the same range of n of n and d. N equal 2 case, he told last week it is proved, but in general case is still open. So using our necessary low bound, so this failureness can be by some several ways. Some computation or existence to showing existence of the degeneration multi-secant plane, but in this case think about this bound. So if this triple Veronese embedding has N7 property, then it should quadric. So this is embedded in pin 9. So codimension is 7. So this should be greater than equal to this number of quadric, and this is 0, and this is so this is 4 times 7 and 28. So it should more than 28 quadrics. But this is, for this case, this embedding is projectively normal. We can show by many theorem, for example, Mumford's theorem. So this is calculated by the easily. This number is and this is give 27. So it cannot satisfy this necessary low bound. So we can show the failureness of N7 of this triple Veronese embedding. Okay. So this is our result. So for last time, I will introduce how to prove all these theorem. I will explain. Okay. So what time I should finish?
Let me see.
Yeah. 15?
Yeah.
20. Yeah.
Yes,
15.
15.
Yeah.
Or 20.
Yeah. Yes. So yeah. I should draw some diagram. So yeah. So please note that. Yeah. So this tall, some rings. Yeah. For example, if you consider the minimum full resolution of this one and just the ideal, then we have the following following relation between this and this. Yeah, so this means beta PQ, this one is equal to beta P minus 1 plus Q plus 1 of these things. Yeah, this is one thing I want to remark. And my notation is, let's just write TPQM for this Tor master. Okay, this is my notation. Then we can consider the following diagram. Okay, so yeah. So we think about two sequences. S1 module, the subring. This one and first this is k tilde 0, and this is k tilde 1. I briefly write down just k tilde 1. Yeah. And consider also, think about some multiplication of the elimination variable. Yeah. Okay. So from this exact sequence, we have some following diagram. Okay. And so yeah, we have this sequence, and from here we also have exact sequence to here by our mapping consequence. So this one is also exact sequence, and vertical and horizontal one also they are all exact sequence. So we can see this is commute. And if we consider the linear syzygy, the first linear strand, then in this diagram we have many vanishings. For example, so our Ix has no linear form, so this is the no linear form. The syzygy of this first one is also vanishing, so this is 0, and this also there is no linear form in this quadrant module, so this is also 0. And yes, and just before of this one also p plus 1 comma 1. This also 0 by same region, so this is injection. Yeah. Okay. And let's denote this is v, and this is mu, and this is nu and mu, and this is pi. And this pi also inject, because we have two. I remind the two basic sequence of the partial elimination theory. So we have this sequence. This is just inclusion. This comes from the multiplications. Yeah. So this map gives our pi. Yeah. So this total module is with this 2 and 3 level. This is exactly approximate by the syzygies of this module. So this gives our free module. So just before this phi map, there is p, 2 and our k2 over k1 minus 2. And if we erase the shifting, then this goes going to be 0. And you see, in our inner projection case, there is no scalar term in k1 or k2. So this is also going to be 0. So this is injection. Yeah, believe me. So we can get the fundamental inequality considers some corner of these two maps. So our diagram is commute. It means these two also equal. So the corner of this one, if our phi is injected, so the corner of this is just this one. This corner is this equals 0, so this one. So beta, the dimension is beta S1 MP, and this one. And also this is this corner included by corner of this one, because so this corner of mu can be calculated. So this one also 0, so can be calculated just dimension of this one minus this one. So this is can be calculated. Dimension, these two dimensions, and we have using that basic sequence again. Then we have this kind of sequence, and using this sequence we can bound the first pattern of this one and the sum of these two ones. So we have the following inequality. This pattern number is less than this one. And this pattern number is okay. Am I right? Oh, sorry, converse. Sorry. Yeah, this is included. The kernel is mu and this is equal to 0. So this included this one. Yeah. So yeah, this is bounded by these two Betti numbers. Yeah. So we have the following. So we have the following inequality. This is and you see this Betti number, it's just erase the shifting. Then this is 1. And this means it is determined by just the linear form of this ideal. So the maximum number of linear form is codimension. So this is not greater than equal to this number. Yeah. Yeah, so if we convert using our notation, then it gives our x is bounded above by this Betti number. Yeah. Okay, so I closed my talk by showing how to using this inequality and to get the maximal bound of the Betti numbers. So I'm sorry for messy notation. Yeah. So here is our x in dimensional. So let's write our x and like this one, and this means denote the codimensions. So this is in here, and draw the time, and this vertical line means codimension, and this horizontal line represents homological degree. Yeah. Yeah. So I think it is good we add one more row. So this line means E equal P line, and here is our given Betti number. So this is 1, 2, this is E0, and this is P0. So P0, 1, and similarly, let's denote in the Betti number the codimension like this. So we want to bound, we want to give upper bound for this Betti number. Yeah. So now we can use this inequality. So this Betti number is bounded by this one, but in a project from any smooth point. So by Betti number, this one and this one, and plus, I denote this is blue chalk, and plus this number. And we can iteratively also give upper bound for this Betti number. Same relation. This Betti number is bounded above by these two Betti numbers. And this one is bounded by these two Betti numbers. And plus E minus 1, and for this arrow, and for this decomposition we have E minus 1, P minus 1. And similarly we can we can iterate this kind of thing. Then here is just one Betti number over here, and this is 2. So this is 2. So this gonna be two arrows. So this is 3 Betti number over here, and this is also 3 Betti number over here, and here is 1. So we can iterate to the state of E equal P. It means this linear syzygy is the codimensions linear syzygy. And in various way, mainly the Green's KPN theorem first part, the maximal number of this Betti number on this diagonal is just the codimension. So we can add all of this number, and it gives exactly the number of this one Betti number of the minimal degree variety. So this is a rough idea. And next case also, if our variety is not a variety of minimal degree, then we have also same theorem for that kind of variety. This diagonal things is 0, not just less 1. This gonna be 0. So we can conversely the sum of these Betti numbers of the minimal degree variety, then it gives exactly this number. So we should subtract the maximal one of this one to get the next to maximal case. And every case and every P, if achieves the maximal equality, then it can be easily reduced to the number of quadric, the quadric station. Then we can give so for example, so if the equality holds, then this means every our inner projection reduction step, the stabilization number is 1 at every reduction step. So if our variety has maximal number of quadrics, then if we projections to the hypersurface case, E equal 1 case, it still has a quadratic. It means this reduction variety is hyperquadric. So the regularity of this one is trivially 2. And by our theorem, S equal 1 case, then regularity can be easily the regularity of this one and this one. So it can lift it up to the original state, and it gives original one is 2 regular variety. And next case is in similarly, if we had some equality, then codimension 2 case, this is the complete intersection of 2 quadrics. Then we can also determine the degree of original one with respect to the codimension. And our depth theorem, so this is the ACM variety, but our depth theorem, we can also lift it up the depths to the original one. So we can conclude our original variety is del Pecho, something like that. It's okay. So I will briefly explain our main idea of the proof. So I will stop here. Thank you.